What we are looking at here is the graph of the function s of t equals negative 16t squared plus 64 on the interval from 0 to 2. This is the function that we were looking at in the lesson for the falling object. The graph will help give us, as graphs do, will help give us a visual representation of what it is we're doing here. So, the first thing we did was we talked about the average rate of change for the entire duration of the fall. Which, since this is a position function, rate of change is velocity, how fast your position is changing, how fast you move from one place to another. So, what we saw in the PowerPoint was that the average velocity over the duration of the fall, starting at the very beginning, time equals 0, and ending at the very end when the object strikes the ground, 2 seconds in, was found by taking the difference in the ending and initial positions over the difference in the ending and beginning times. These values can be obtained from the function, but at least in this case, the height or the position at the very beginning and the height or position at the very end are both very easy to get just from the context of the problem. At 2 seconds in, the object has struck the ground and is at a height of 0. And at the very beginning, before the object is dropped, or rather at the exact moment it is being let go, it is 64 feet in the air. This gives us negative 64 over 2, which is negative 32 feet per second. Now, visually speaking, this is what that looks like on the graph. Here is the point up here, 0, 64. That is the initial time and the initial height. And down here at the very bottom is 2, 0. 2 seconds in, the height is now 0. So, the average rate of change calculation looks an awful lot like the slope formula because that's what it is. It is the slope of this line. We go down a total of 64 and right a total of 2. Now, this is where the visualization becomes very handy here. This assumes a constant velocity, which is definitely not true. Anytime you've ever thought about a falling object, or any of you guys have ever gone, skydiving, or tossed an object up in the air, it moves faster at certain points and slower at others. In this case, since we're not tossing something up in the air, we're just dropping it, it has virtually no velocity at the beginning. That is to say, if we were only look at a very small portion up here, we see a very small change in the position of the object because it is falling very slowly, relatively speaking. Meanwhile, at the very bottom, if we were to look at it here, it is on a much narrower portion of the interval, a much narrower, much smaller section of time, falling a greater distance. So it is definitely moving more quickly towards the bottom. It will continue to gain speed as it goes. We are, of course, ignoring wind resistance here, so we don't have to worry about terminal velocity or other extra complications like that. So the problem here is, if we want to talk about how fast the object is moving at the very end of the fall, right when it's hitting the ground, right when it's going its fastest, then values of the velocity towards the beginning of the fall are very, very small and are causing the average to be very inaccurate. Actually, visually speaking, notice the amount of space, the size of that region in between the line and the parabola. Not very close to each other, relatively speaking, of course. there's a lot of room in there for improvement. So what if we try this? What if we recognize that the earlier portions of the fall are the slowest, and therefore are skewing our estimate of what's going on at the very end, at the fastest portion of the fall? And what if we decide that instead of a line between 0,64 and 2,0 spanning the entire 2 seconds of the fall, what if we ignore the entire first second? What if we find the average rate of change of the function, not on the entire duration of the fall, but only after the first second, from t equals 1 up to t equals 2? Note that portions of this will remain the same, and other portions of it will change. S of 2 is still going to be 0. It's still on the ground at 2 seconds. S of 1 then is asking, how high up is the object 1 second into the fall? Well, we can get this value from the formula simply by substituting the value of 1 in for t and evaluating the function. If we do that, we should find that the object is still 48 feet above the ground 1 second in. So note that in the first second, it's only fallen 16 feet. In the next second, an equal period of time, it has to fall 48 feet. It has to go considerably more distance in the same amount of time. That supports our hypothesis that it is moving faster towards the later part of the fall. Note that in the denominator, the change in the left endpoint of our interval is changing what is going on in the denominator, so that we actually have a different value in the denominator. We get negative 48 over 1, which is, of course, negative 48. Now, like before, what we can do is we can draw in a line segment connecting the 2 points at each end of our new interval. Our new interval does not cover the entirety of the fall. It begins at this point here. Now, note in the calculation, we actually found a steeper slope, or a larger slope, which should result then in a steeper line. And sure enough, we have a steeper line than we did before. Not only is it steeper, notice that it is much closer to the actual parabola. We had a large gap of space before. Now we have a very narrow gap of space. This is a much better estimate to what's going on towards the end of the fall, because we excluded that slower portion at the beginning. Well, it's still not perfect, though. I mean, definitely, visually speaking, it is much, much better. But, while not as obvious as before, it's still going slower here than it is down here. So while it's not as obviously flat like it was at the very beginning, it still is not as fast. If the idea is that it is gaining velocity as it goes, then it must, by definition, be moving more slowly at 1 second than it is at 2 seconds. So if we improved our estimate before by cutting off an earlier portion of the fall, then perhaps we can do it again. Instead of covering the entire second, if you will, of the fall, what if we cut off the beginning part of that and we only look at the last half of a second of the fall? This should give us a better estimate. I imagine some of you guys can already see what's unfolding here. What we're working up towards is a limit, where the left endpoint of this interval is going to approach the right endpoint. Little bit at a time. So just like the very first lesson on limits, on an introduction to them and finding them numerically, we're starting with, we're starting with simple values. And remember again, the numerical method is solid, but very slow. It was a good place to start before because it was easy to work with the concrete values as opposed to working with the graph. I mean, while we are looking at that here, it's hard to identify actual values from the graph. It's hard to identify specific values from the graph. These two might not be so bad, but once we start getting to some decimal values, things are going to get a little bit hairy graphically. So the numerical method is very solid. It will always get us there, but it does require the most amount of calculation and work. It is, again, not adaptable to other values. It is really good for finding, we seem to be targeting 2. It's very good for targeting a single input value, as we'll see. But not so much for when we're trying to do a bigger concept. So again, these values can be obtained. The ones we already know, of course, S of 2 is 0. And S of 1.5 can be obtained, again, by using the formula here. Since we happen to have that point marked on the graph, we can tell that the y-coordinate there is 28. Note that, again, in the denominator, we have a different value for the beginning of our interval. That's relevant, of course, because it reflects the total amount of time. We're only looking at the last half of a second. Now, this is a very friendly function so far, and it has produced some very friendly average rates of change, or velocities. That is going to end very soon, because as you might recall with limits in the previous chapter, we end up having to go a great deal closer to our target than just one whole number away, or 0.5 away from it. Now, the graph is going to start to become less and less helpful as we go here, because that new line segment here is incredibly close to the parabola. But again, it's all a matter of perspective. It is incredibly close to the parabola on this scale. The scale here is actually fairly large for the y-axis. We're covering a great many values in a small section of space compared to the x-axis, where we're covering only 2 whole numbers, only 2 integer values over a large amount of space. But even then, we have to get much, much closer than this. As we saw in the first lesson, it's all a matter of perspective. 1.5 is pretty close to 2. But there's a lot of space in between 1.5 and 2. So, what if we recognize that as close as that is, it's still slightly slower here than it is at the very end? And we say, okay, if we keep cutting off portions near the beginning, what if we get down to the last 1/10 of a second of the fall? We're now in the last 1/10 of a second of the fall. And at this point, we kind of have to use the calculator. There's really no way that we're going to be able to get the value of the function at 1.9 without it. The graph is not going to be reliable here. So we have, as before, its height is 0 at the very end. 1.9 seconds in, it should now be very close to the ground, and in fact, it is. it is now only 6.24 feet above the ground. So it has to fall that remaining 6.24 feet in the last tenth of a second. And that gives us negative 62.4 feet per second. Okay, so we've now left the realm of friendly output values, or friendly values for the average rate of change. But, as we've seen with limits previously, that should not really be a surprise. Now, I would attempt to draw this in, but if the previous line was that close on this scale, this new line segment would be unbelievably close, really indistinguishable. I would have to draw a much more zoomed in graph that focused on just this small area and blew it up to the size of the page or bigger so that we could actually start to see the difference. Well, that's great, but we know from limits 1.9 is close to 2, but there's still an awful lot of room in between. So what if we get down to the last 1/100th of a second? Now, we are going to calculate that, yes, but again, what do we know from limits? We probably are going to have to go closer even than that. So what if we go down to the last 1/1000th of a second? Now, with limits, it is always best to look at them in terms of a table. So on the side over here, I set up a table. This time, however, we're not looking at input values and output values. This time we're looking at input intervals. The average rate of change is not a calculation done at a single point. It's done over an interval of values. In this case, the 2 has stayed fixed, and we are always moving that left endpoint closer to the 2. So I gave it an x as the left endpoint. So what we have here is for our first interval, we have 0 to 2. Then we moved it closer and we did from 1 to 2. Then we moved it even closer and did the last half second of the fall. And then the last tenth of a second of the fall. And then the last 100th of a second. And the last 1/1000th of a second. Now, as with any numerical limit, we can continue this as far as is necessary to establish the pattern. Now, I'm going to throw these values in there, but again, thinking of numerical limits from previous lessons, these values up here are kind of far away from 2, considering how close we're going to end up getting. So these are probably not going to be very helpful in establishing the limiting value of the average rate of change. That will probably come from what we see further down the list. Now, we did not do the calculation on the page here. I leave those to you to do. They are done in very much the same fashion as the others. But what we get out of them is that the average rate of change over the last 1/100th of a second is negative 63.84. Make sure I have that right. Yes, negative 63.84. If we go one step further, down to the last 1/1000th of a second, we get negative 63.984. Now, at this point, we've probably gone far enough to start suspecting, even being fairly certain, what this is approaching, especially with these last 2 values, because so many of the digits are the same. In fact, the only real difference is in this last 1/1000th. It's almost like an extra 9 was stuck in between the decimal point and the 8. We've seen that style of pattern in the digits before, so this is somewhat recognizable, and the example was chosen to be so. What we could do then is to confirm our suspicions, go one more level in, and perform the average rate of change calculation for the last 1/10,000th of a second. And sure enough, if we do that, we get negative 63.9984. Another 9 has been slipped in between the decimal point and the 8. I would think at this point it's safe to assume that if we continue the pattern of getting closer to the 2 by decreasing powers of 10, that we're just going to continue to see additional 9s stuck in there until eventually we're looking at negative 63.999999999, etc., with a trivial 84 at the end. So we're approaching negative 64. What we might say then is the limit as x approaches 2 of the average rate of change from x to 2 is equal to negative 64. This is what the derivative is. The limit of the average rate of change of the function on an interval.